In this video, we'll be taking a look at problem 34 on page 103 in Giancoli. We're going to be looking at the net force on each of the blocks A, B, and C, as well as the contact forces between the blocks. I'll be using general analysis of multiple body systems, as well as some object-agent notation to analyze the system. First, a reminder on how to use object-agent notation. Suppose we were interested in looking at all the forces acting on block A. We'd make a free body diagram on block A by reducing it to a dot and then having all the forces extending out as arrows that are acting on block A. Notice that all of the forces on this diagram start with an A. For example, the force on A due to the earth is the weight vector. The force on A due to the surface upward is the normal. The force that block A is feeling due to the push is FAP over here. And the force on A due to B is this force labeled over here on the left. The object-agent notation will be really useful for this force, maybe not so much for the others. So I'll be changing some of those labels as we go throughout this exercise. For example, this one I will write as force weight for A. This one is just the push, and this one is the normal force acting on block A. The first step in analyzing any multi-body system dynamics is to draw a free body diagram for each object in the system. Take a moment, pause this video, and please draw a free body diagram for each of the blocks in the system. Here's what I hope you have drawn for your free body diagrams. I already did discuss the one for block A, so we'll just move on to block B and take a look at the difference. We have a normal force and we have a weight vector, but we have a backwards opposing force on B due to C, and we have a forward force to the right here on B due to A. The free body diagram for block C is quite different because it only has a forward force, or force to the right, on it due to block B. There is no opposing force because this system is frictionless. The next step in the analysis is to create a net force equation for each block. Please create a net force equation for each block. Notice that this entire problem is abstract at this point. We do not have any numeric values to insert, so just leave everything in terms of variables. Here are the net force equations for each of the three blocks. Notice a few things here. First of all, if we had numeric information, we could solve for the force on C due to B. By Newton's third law, the force on C due to B should be equal and opposite to the force on B due to C. So if we were to figure out that force, we could plug it into here and figure out, based on other information, if we knew the mass of the block, for example, and the acceleration of the system, what the force on B due to A would be. And then we could use that and Newton's third law to connect that over to the force on A due to B. Another thing to take note of in this kind of a situation is that the acceleration of each block is equal. If we know the acceleration on block A, we know the acceleration on block B, and we know the acceleration of block C, and so on. They are all equal. So we've been able to create net force equations for each of the blocks in the system, but what about the net force of the entire system? Remember that the net force on the entire system is all pushes positive minus all resisting forces negative. So please write out a net force equation for the entire system. Okay, so our net force equation is all the pushes minus all the resisting forces. So we're considering the pushing force that's on that left, plus the force on B due to A, plus the force on C due to B, and then the ones that are pointing backward are the force on A due to B and the force on B due to C. Of course, you notice what's going to happen next is that a lot of these forces are going to drop away when we begin making substitutions. F net is just ma, so that's the mass of A plus the mass of B plus the mass of C multiplied by the acceleration of the system. And we're going to set that equal to, well, BA and AB go away because of Newton's third law. CB and BC go away because of Newton's third law. And of course, the net force acting on the system is just the pushing force. So we can use this net force equation to figure out what the acceleration of the system is. It's just the pushing force divided by the sum of all three masses together. Now in this particular problem, they eventually go on to tell you that the pushing force is 96 newtons and that the boxes all have equal masses of 10 kilograms. So 10 plus 10 plus 10 is 30 kilograms. So that means you can solve for the acceleration of the system. Once you know what that value is, you can go back to the previous page with all the net force equations individually for the boxes and figure out what the force of on A due to B is and what the force on B due to C is, and that gives you the internal forces between the boxes.